This is the Monismith Lecture in Pavement Engineering. It is a brand new award. New ASCE Lecture established under the auspices of the Geo-Institute. Professor Monismith's career highlights: served on the CE faculty of Berkeley for more than 50 years, pioneered mechanics approaching and flexible pavement design, distinguished member of ASCE, NAE member, of course, 1980, National Association of National Academics 2001, National Associate, of National Academics, Berkeley Citation 96, the TRB Roy Crum Award 95, the James Lohr Prize 88, ASCE State of the Art of Civil Engineering Award 78, TRB Woods Award 72, AAPT Emmons Award 61, 65, 85, NAPA Hall of Fame member, ISAP past chair, served as a consultant of various organizations, U.S. ACE, Trans Canada, U.S. Air Force. So as it says at the bottom, he is a true father of pavement engineering. The lectureship creation, a fundraiser effort led by the GI Pavements Committee. The necessary endowment was raised with individual and corporate donations. List of contributors follow. And I'm not going to read them, but I will leave it up here for you all to see. So the award, the criteria for the award, be awarded annually to an individual for significant contributions in pavement engineering. Nominations can be made by any GI or ASCE member or technical committee. Nominations are evaluated by the GI Awards Committee. Final approval of awardees rests with the GI Board of Governors, and lectures will be delivered at an appropriate conference each year. So the first awardee is Professor Monismith himself.
Well, before I start, I'd like to first thank the Pavement Committee for establishing this award. I think it's very important that pavement engineering be brought to a higher status within the geotechnical field. Secondly, I'd like to thank the committee that generated the funds. Gary Hicks was the sort of the charger, but Rita Lay and Jeff Hilliard were involved too. So if they would just stand for a minute, I'd like to just thank them. And I'm going to talk a little bit about the developments prior to 1960 and then mention mechanistic analysis briefly, materials characterization, pavement design, accelerated pavement testing, which has become a very important part of the process, non-destructive pavement evaluation and overlay design, improved construction, which if pavements are not properly constructed, then everything goes to the devil. So, and then briefly pavement management, which has become very important in making sure we take care of our systems. And then I'm going to make a few observations on pavement engineering education and training. I think there are some developments. I've just picked a couple of these very important developments, particularly the Corps of Engineers, 1940s, 50s, the work that they did at the Waterways Experiment Station, the use of Busenesque analysis, for example, in pavements, full-scale testing, 13 test sites around the United States, the use of the CBR in this case because there was nothing better than that at the time. Then the second was the test roads in the U.S., particularly the Washoe test road in 1952, and then very importantly the Ashoe road test, which really sparked the interest in pavement design again from about that period of time. And then of course also in the late 40s, early 50s, the UK was doing a lot of studies of in-service pavements. And one of the key people at WES was Dick Alvin, and of course, very importantly, Bill Turnbull, and he had been a very, very important part of the group. And the Ashoe road test really, as I say, sparked the whole process. And the man in charge of the engineer in charge of the program was Bill Carey. He was the engineer on the job, and he really did a very good job. He shielded his engineering staff from a an advisory board that wanted to do many, many things. He really did a great job. He also became chairman of the chairman of the Transportation Research Board, or whatever you call the director. And then Sir William Glanville was the director of the Road Research Laboratory, overlooking some of these people who did the road studies. And one of these was David Croney. And he also, and Glanville, participated in an event that I'll be talking about in just a minute. And then a very important person that made significant contributions is right here in California. That was Francis Veeam. And he introduced the idea of load equivalencies. It really didn't start with the ASHO road test, but rather with Francis. He stressed the importance of the tensile characteristics of the pavements. Before, there was nothing given to the asphalt concrete. They just put so much above the subgrade. And then he brought about this development of the concept of fatigue in pavements. And I think one of the classic papers in pavement engineering and soils is his paper in the TRB. This is Francis Veeam, materials engineer for a number of years. And in this particular case, in looking at the slide, you'll see the two A figures and then the B figure. The B figure was very low deflections and heavy traffic, but no cracking. And then the other was higher deflections, and again, small traffic in the passing lane, but heavy traffic. And so this really sparked the idea of looking into the fatigue of asphalt concrete, which then led to this whole process of mechanistic empirical pavement design. And then really what sort of gelled everything was the International Conference on the Structural Design of Asphalt Pavements in 1962. This was held at Ann Arbor, Michigan, and many people from around the world came to this conference. It was sponsored by the Asphalt Institute. Jess Buchanan was the president. Fred Finn was really the workhorse at that time, and he had been the Asphalt Institute representative on the road test. And then they worked with Bill Housel and Ward Parr and developed a conference that really got the whole thing going. This is Jess Buchanan, Fred Finn, younger period, Bill Housel, Ward Parr. And then some of the early U.S. participants, Gene Skoke, had actually worked on the road test and was involved then at the Asphalt Institute before he went to the University of Minnesota. Bill Getz, Purdue University, L.D. Yoder, Purdue University, and then some international participants, Norm MacLeod from Canada, Nybor from the Netherlands. I can remember I met him at the lab, and I went home and I told my wife that this is the hand that shook the hand of Nybor. And she said, so what? So. But he was a great pavement engineer. And then Cor Wester, the Dutch Study Center, and Knockel from West Germany, Kirk from Denmark, Rigdon from South Africa. These are all very important people that contributed to the development of pavement engineering. And sort of the way we look at pavement engineering today then is that we have to have inputs, we have to have distress analysis, and then design decisions. So we have to look at traffic environments, subgrade, material characteristics, construction considerations, degree of risk, and of course we have to consider the effects of frost. And today the primary modes of distress are fatigue in the asphalt concrete, or possibly in other treated materials, rutting and thermal cracking, and then also, particularly for overlays, reflection cracking. And so you put this all together and you find out how best combination of materials can be attained and developed along life pavement. And so in the case of the development of asphalt pavements, very simplistic representation is a structure of this type. And we have the tensile strain at the bottom of the asphalt concrete or some treated layer. And in this case, we show the vertical compressive strain at the surface of the subgrade. And many of the design procedures that were evolved from a mechanistic empirical standpoint were built on these principles. And so one of the important analyses then that developed was the ability to look at multi-layer elastic analyses. And Burmester had done this in the 1940s, but we didn't have electronic computers at that time. But in 1965, Chevron developed a multi-layer program that was very effective. I don't think they really received the proper credit for this, but they developed this, and this led to the program LSIM and then other developments. And then, of course, viscoelastic analysis was introduced by the FHWA, finite element analysis. Mike Duncan and Ed Wilson started the axisymmetric 2 and 3D idealizations, and then some of this lent to the ILI-PAVE being used as a part of pavement design today in Illinois. And then dynamic analysis, and Kareem Chamini was one of the people working in this area. So, but this is a picture of Burmester. Then, and then of course now programs today, we have a lot of them that work on the computers, BISAR shell, LSIM, Julia, which is a part of the MEPDG in the United States now, and also Federal Aviation Administration, CERCLI, Australia, ILI-PAVE, Illinois DOT. Now, in terms of the material characteristics, we can start with the asphalt. And here, this material is a nonlinear, rate-dependent material. So how do you treat it? Well, we treat it in terms of stiffness, where we take into account the effects of time of loading and temperature and try to utilize that information in the design using primarily elastic systems today in the design methodology. And some of the key people were doing this in early 1950s, Vanderpoel and then Hukelom and Klomp. And of course, the untreated materials are also nonlinear, not so much rate dependent, but we still try to, in an ad hoc manner, use properties that we get from laboratory testing or from field testing to get a measure of moduli that we can use in these multi-layer elastic analyses. And some of the people involved are Harry Seed, Steve Brown from Nottingham, Marshall Thompson, George Dalen, Gary Hicks, and Dick Barksdale. And generally, when you look at the stiffness of asphalt mixes, the behavior at very short times of loading is about the same as concrete, and at high temperatures, and of course, longer rates of loading or longer times of loading, then the moduli drop off. And you can see how this happens. The temperature T0 in there is the highest temperature, and T2 might be something much less. And this is Hukelom, another great engineer from Shell, KSLA in Amsterdam. And today, of course, one of the types of equipment that we use to measure the modulus of the asphalt concrete is the dynamic axial test, repeated loading, or sinusoidal loading. This is on the left. And then the diametral test is also used to get measures of stiffness at low temperatures. Now, in the case of fine-grained soils, we realize that we have to consider the water content, dry density, soil structure, the applied stress, and today we measure it usually in terms of repeated load axial test and a resilient modulus developed. Actually, Harry Seed introduced this in the early or late 1950s. And of course, we have to consider then, particularly not necessarily saturated soils, but partially saturated soils. So we have to also look at the matter of suction and then freeze thaw. And in the case, as I say before, the modulus of resilience is developed from repeated load tests, where you take the deviator stress divided by the recoverable deformation. And Harry Seed, of course, was a good soil mechanics person, but I show my age when I talk about soil mechanics rather than geotechnical engineering. So. And he started the resilient modulus testing, and his work led, of course, to then the dynamic loading that got involved for liquefaction. Steve Brown did work for looking at various states of stress, including suction. Marshall Thompson did very good work on the freeze-thaw behavior of soils. And of course, very importantly then, we have to recognize that when we're doing the materials for pavements, specimen preparation is very important. And of course, what are going to be the conditions? Well, the Corps of Engineers for the CBR test use saturated soils. But we have to realize that many soils don't become saturated. And the Australians and the UK Road Research Laboratory did a lot of work on measuring soil moisture suction and for partially saturated soil. So some of the designs that we use are based on soil moisture suction considerations rather than saturated soil behavior. And then fine-grained soils are, of course, the structure and related to compaction. And Lamb and then Mitchell at MIT developed the idea that soil structure in fine-grained soils is very important, and this affects the stiffness characteristics of the materials. And so Jim, of course, is sitting in the room today, the earlier picture. Then for the untreated granular materials, we have to recognize again that this is a nonlinear material, but a modulus, again, measured in a repeated load type test, is a function of the sum of the principal stresses. And of course, dry density has an effect, the degree of saturation, and the aggregate gradation. And some of the people that did work in this area were George Dalen from South Africa, Gary Hicks, who's sitting here in the audience, and Dick Barksdale, who unfortunately died at an early age. And so then the next thing that we have to do is we have to take this information and put it into these analyses to make distress analyses. And so the three that I've mentioned to you are fatigue cracking, primarily hot mix asphalt, permanent deformation, rutting, thermal cracking, primarily low temperature cracking. Well, in the case of thermal cracking, primarily the binder selection has become very important today. And with the with the new grades of asphalt that we have mitigated to some extent this problem of thermal cracking if you choose the proper materials and you properly compact the pavements. And so in the fatigue test development, this occurred both in Europe and the United States. Shell supported the work at Nottingham, and Peter Pell, one of the really very important people in this area, and R.N.J. Saul was from the Dutch KSLA. And then we got started the work in this area, and partly because of the work that Francis Veeam had been presenting in that paper. Ken Secor, Jack Deacon were also involved. This is Peter Pell, Jack Deacon, a recent picture. And then the fatigue testing also expanded. Shell did a lot, Hukelom and Klomp, Van Dyke in the 70s. France did a lot of work, the LCPC in Paris, the Asphalt Institute, and then others, for example, the CSIR in South Africa, and we'll see more of that a little bit later. And some of the equipment that is in use today, this is the device where you have essentially a cantilever with a pyramid so that the specimens are will not fracture at the ends, but someplace about halfway up the beams under the repeated loading, sinusoidal loading in the test. And these are two pieces of equipment developed during the SHARP program. This 4-point bending, this is the Cox equipment, and this is the Australian equipment. This one is servo-hydraulic, this one is actually servo-pneumatic operated. But these are based on the designs that Jack Deacon had developed years ago and just made larger for today's testing. And then it so happens that the fatigue of mixes can be inversely proportional to the stress or the strain. And normally we use the strain. It's a measure that we can actually look at. And they say happiness is a straight line on a log-log plot. And so in this case, at least over some range, the strain is proportional logarithmically to the number of cycles to failure. Normally you should plot this the other way because strain is the independent variable and NF is the dependent variable, the cycles to failure. But we use that then in design, and we have, of course, temperature effects that we have to consider because asphalt is a thermo-rheologic type material. And as the stiffness increases, as you look at the slide there, the strains at break go down. And so generally we have an equation of the form that you see I hope I pressed the right button here. Yeah, this where the cycles to failure is a function of the strain and the stiffness of the mix. And there are other factors that will be involved in this as well. And then, of course, the problem is that traffic is going to have different load levels. And so how do we combine these? And the concept of the linear sum of cycle ratio, some people refer to it as Miner's hypothesis, was suggested by Ken Peedy of Shell. And actually Jack Deacon then did a very detailed study looking at load effects in different sequences. And it seemed to be reasonable. And then, of course, the effects of temperature were such that one could actually interchange with temperature as well. And this was done by people at Nottingham. So as a consequence, one then could actually sum for example, if we take the number of loads to failure here, and these are the actual loads applied, then of course the ratio of N3 to N3 is sum damage. And when that damage sum reaches 1, then of course you have supposedly cracking. Now some people argue that this is not a very good system, but it works from an engineering standpoint. And you have to realize that in any kind of field, when we're doing designs, we have to think as engineers and not as scientists. And we have to make sure that we can get something that is going to provide a reasonable answer. And this seems to do that. Now, the problem is, in the case of fatigue, it turns out that once you get to very low strains, there seems to be a change in the slope of the line. So some people have called this an endurance limit. And so at least for conventional asphalts, it looked like it was in about the range of 70 to 60, 10 to the minus 6 strain, and around 100 million repetitions. And so people have been looking at that more recently, and very nice work has been done at Illinois by Carpenter and the NCHRP projects. And these studies have indicated that maybe, depending on the type of binder in the mix, there may be different strain levels where this might happen. And of course, then we always have to throw in a booger factor, and we call it a shift factor, to relate the behavior in the laboratory to the behavior in the field. And so some shift factor format is developed, and we relate it to some percentage of cracking in the field. Normally, in the case, for example, of some procedures up greater than 45%, others 10% or less. And normally when you get up to about 10% cracking, the pavement is sort of on the verge of failure. Now, this is one of the first works supported by the NCHRP to look at mechanistic empirical design, and it turned out that Fred Finn developed the relationship that eventually was also used by the Asphalt Institute, and you can see then the inverse ratio to strain, the inverse ratio to stiffness, and the fact that when you look at 10% cracking versus 45% cracking, there's about a 40% difference, at least for the data that were available at that time. And these were based on thicker pavements, 4 inches or more. And then Matt Witzak, when the Asphalt Institute adopted this formula, then added the capability to bring in the effects of the asphalt content and the degree of compaction of the mix, which is a very important consideration. And this is an early picture of Matt, some of you knowing today. And then the fatigue relationship today used in the MEPDG has this form of, there is a factor for the mix volumetrics, as you see, the strain, and the stiffness. So this is a design relationship that seems to work pretty well. Now, permanent deformation is also a factor that comes into play, and we have to make certain that when we look at the pavement components, that they are not going to contribute very much to the deformations at the surface, because if you develop rutting and you have rain, you have the possibility of hydroplaning. And so as a consequence, we have to be very careful about that. And in the case of the untreated components, the load stresses, shear stress at the surface of the asphalt or the aggregate base and subgrade are a factor. Another factor that has been used that I've alluded to in the past is the vertical compressive strain at the surface of the subgrade. And this was suggested by Dorman at the 1962 conference. And Shell really had, at that time, a scheme in mind for a mechanistic empirical design procedure, which involved the vertical strain and the fatigue in the asphalt concrete. Then for the asphalt concrete itself, primarily shear deformations occur that lead to the rutting, and this is in the upper part of the pavement surface, the upper 4 inches in highway pavements, probably a little thicker for airfield pavements. And this can be controlled primarily by mixed design and construction, but we still have to make some estimates of the actual rutting that might develop. So in this case, this represents the subgrade strain criterion that the format that the Shell people had suggested. And it turns out again that there is sort of a linear relationship up to a certain point again, but when you get to greater than about 50 million repetitions, it seems to flatten out again. So these can be considered then as a part of the design procedure, and if you're going to be developing long life pavements, then you might think in terms of the endurance limit in the asphalt concrete, and also this endurance limit in terms of the contributions of the untreated materials to the deformation at the pavement surface. And Gil Dorman, actually, he and Harry Seed were colleagues at the King's College in London there back after World War II. Now, the prediction of permanent deformation, there are a number of procedures that are being developed, but one that is in the, at least as I understand it in the MEPDG, is what is called the layered strain procedure, and I'll briefly show you that. And then there are others, such as was developed during the SHARP program and at the West Track. And then, of course, there is this matter of cumulative damage, or the accumulation of repetitions of permanent deformation in the pavement structure. And this represents sort of a very quick schematic. What is done is to actually look at the state of stress and calculate a plastic strain developed again from repeated load tests. And you do this through the various components. You sum the components of each layer, and taking that sum, then you arrive at the rut depth at the pavement surface. So it's just a pretty direct procedure looking at the states of stress and the plastic strains that are developed in the pavement materials. And then, of course, compound loading is an important process again, as we had shown in terms of pavement fatigue. And so in this case, the time hardening concept taken from metals has been used, where you have say different strains where you show the number of load applications plus the inelastic strain. And you can, if you have one load application, you move up the curve. And if you have a different one, then you add to that and so forth, back and forth. And this is actually built into the MEPDG again to look at the cumulative effects of traffic on pavements. This was suggested by Charles Freem back in the early 1970s from South Africa. And Shell quickly picked that up, by the way, and built it into their mechanistic design procedure. The other is the use of the elastic shear stress and shear strain. And the procedure then involves calculating permanent deformation for a given stress and a given elastic strain and a specific number of repetitions, and then you just sum that. And in this case, through finite element analyses, the rut depth is just equal to some coefficient times the sum of those plastic strains, and this is only in the asphalt concrete. So this would be a way of looking at the asphalt concrete, and then if you have a well-designed pavement, if you use the vertical compressive strain concept at least, you get a very small contribution at the pavement surface because of the underlying materials. Now, low temperature cracking, there is a prediction in the new design guide. It involves the indirect creep and tension test. It involves the thermal stress restraint, or it involves just the indirect creep and tension test, and an analysis procedure developed that is in the MEPDG. Another way of looking at low temperature cracking is the thermal stress restraint specimen test. One of the men in the room that was very involved in this, Ted Vinson, actually developed a test that was very helpful in looking at the behavior of mixes, where you actually restrain the mix, drop the temperature, and eventually you get a thermal stress that's going to crack the mix. And this seems to work pretty well too, and many people are, particularly in Europe, are using this as a part of their design methodology for looking at the behavior of mixes at very low temperatures. Now, the mechanistic empirical design analysis, or design and analysis, actually the US Navy had a procedure using the Burmester work in the 1940s. But really, the key that have developed since then are the shell. This would be Dorman and Peaty, and then the shell pavement design procedure. Fred Finn and a group actually developed a sort of a system which was a forerunner of the new ASHTO guide. This was in the late 1960s, early 1970s. And then, of course, we now have the new mechanistic empirical design guide. And, of course, Matt Witzak played a very major role in the development of that. Pim Visser was the person that Shell that was in charge of the development of the Shell Pavement Design Manual. The ASCE Pavements, of course, we have the Asphalt Institute, and there Jim Shook, Matt Witzak, when he worked for the Institute, Fred Finn, Larry Santucci were involved in the development of the current, or at least the framework for the current design manual. And then the LCPC also developed their design procedure. Belgium, just as an example. I haven't picked all of them, but I'll show you a few of these. This is Jim Shook at a younger time, Larry Santucci, and one of his contributions to this was the fact that he had done a very detailed study at Chevron on the fatigue characteristics of asphalt emulsion treated materials, which Chevron, of course, did sell a lot of emulsions at the time. And so this was built into the Asphalt Institute design procedure based on his work. And then a couple of the people involved from France, there are many of them, but I've just picked two. Sauteré was one of the early, and he was involved in the conference there at Ann Arbor. Jacques Bonneau, a major player in the field for a number of years, and of course he really was very instrumental in bringing the LCPC method to what it is today. And then Verstraeten from the CRR in Belgium actually did a lot of work initially on mechanistic analysis and then developed their design procedure. Now, other examples, the CSIR in South Africa. It's interesting, a small country like this has one of the best research programs in the pavement area in the world. And we were very fortunate in the 1990s to begin working with them. So they are a part of the research team now that exists at Davis and Berkeley. And some of the key people from the CSIR were Charles Freem again, Neil Walker, and Hoffy Marie. The NASRA, the National Association of State Road Authorities, has their procedure. Illinois, and by the way, if you want to see a very good design procedure, mechanistic design procedure, look at the Illinois DOT procedure. It's relatively straightforward, but it's all based on mechanistic empirical design. So I would suggest that some of you from state highway departments want to take a look at that. And this is Neil Walker. Unfortunately, he died at an early age. Hoffy Marie is still with CSIR. And then, of course, very importantly, we have to recognize the matter of reliability. And for ideal pavements, we like to design to a high level, normally in the range 99 to 95%. And fortunately, today we have the ability to do this because we can develop information on the materials, construction, and traffic variants that might exist. And the use of Monte Carlo simulation then allows us to actually do this. I say we, and people say, where do you get this we business in? So yeah, I can't do it, but other people can. So, and non-destructive testing has become a very important part of our process, because many of our pavements today are being just redesigned or overlays placed. And so one of the things that happened was at the Asho road test, a man by the name of Benkelman developed the Benkelman beam. And he did that originally at the Washoe road test, perfected it at the Asho road test. And then in France, a device called the traveling deflectometer also was developed, or deflectograph, and people at TRL really made it work very well under Norm Lister's direction. And California also developed a traveling deflectometer that they used for a time, but it no longer is used, and that was developed under Veeam's watch. And in the case of vibratory testing, the Shell people started back in, again, the 1950s using a heavy vibrator, and they assumed that all the waves in the pavement from the vibrations were shear. Well, it turned out that they're not, and the wave propagation work of the TRL really began to take advantage of the seismic studies looking at Rayleigh waves, shear waves, and P waves, or compression waves, and trying to interpret those then as you vibrated the pavement at different surface frequencies. And these would allow you then to actually get measures of the moduli, or stiffness, of the various layers. And then there was also another device developed in Texas called the Dynaflect, and this was used for years. The problem with it is that it provides a relatively light load to the pavement surface. But what has happened then, since these other developments, falling weight deflectometer was developed in actually France, but Denmark really made it work, and then the Shell people also developed it to an extent where it could be used in very practical applications. And so this is the device that really is used today to measure pavement deflections, and then, of course, use that information to calculate, by back calculation procedures, the moduli. This is a picture of Benkelman. He liked to play poker, and he played what we call a wee peaky or something like that. So, this is Norm Lister, odd clomp. Overlay design, normally, when we started this early on, it was based primarily on deflection measurements, and one of the real good design procedures developed at that time was by Lister, because he built reliability into the design methodology based on their analysis of deflection data. Then the FWD, and of course, allows us now to measure the basin, actually measure and calculate stiffnesses in the various layers. And a very good example of this is the WashDOT HMA overlay thickness design. Accelerated pavement testing has provided us a way of arriving very quickly at behavior of stuff that we think about in the laboratories. And of course, we have South Africa, Australia, and a number of these pieces of equipment are now being used in the US. This is a picture of the HVS. Steve Kuhn in South Africa was the developer. Construction considerations, and I'll just note here that compaction is so important that you have to make sure that you do compaction, but at the same time, you also want to ensure that when you put materials into the pavement, you want to go to the target value, like in this case for asphalt content. You want to have very low standard deviations so that you have good pavement performance. And you can see if you change the compaction, you take away life of the pavement. And then pavement management, of course, we have a number of systems. Fred Finn, again, was very, very important in the development of that. And Ron Hudson, Ralph Haas, these all started together about 1970. And then Roger Leclerc really made the one at WashDOT work. And then, of course, the role of pavement management is important to us to help us to look at the behavior of pavements and then improve our designs as we go along and make good decisions rather than just doing this and that to take care of the pavement. Now, some observations. Considerable progress has been made since the 1960s. And this has resulted, as you have seen, from international cooperation and sharing of knowledge. Many people have been involved, and they're good people. They really are good engineers. And the technology now is available to design, construct, and rehabilitate longer-lasting asphalt pavements. But well-educated engineers and technicians are required in the pavements area to properly accomplish this. And so education and training is important for engineers, technician, and construction maintenance personnel. And one of the things that concerns me is that many of the universities in the United States are no longer teaching pavement engineering. And I think that's bad because we spend over $100 billion a year on pavements, just in the United States. And so the solution is that you have to actually make sure you have trained people doing the job. And you have self-managed learning, technology transfer, and it involves not just the engineers, but the technicians and the construction personnel. So I thank you very, very much for this opportunity to make a brief presentation. Thank you.